All right, welcome back to Mr. PL's with Algebra 2. This is Unit 1, Topic 1, SLT3. Starting off with the warm-up. Find the inverse of f of x. Inverse of negative 13.5 would be 5, negative 13. Because as we have talked about in prior SLTs, inverse means literally it is just to flip the x and y, but what it really means is that whatever you started with here in the original function is what you should end with in the inverse of that function, or the inverse relation. And wherever you ended the first function is where you should begin in the second function, or the second relation. So negative 9 here. My pen's not working out so well, so I'll just say it. So this would be negative 2, negative 5, negative 5, negative 1, negative 4, 0, 6, 4, 10, 9, and 32, 14. Okay, so maybe it wasn't that bad. The function is shown on the graph. Graph the inverse of f of x on the same set of axes. Okay, f of x is shown on the graph, so graph the inverse. So first thing we need to do is label where the points are. 1, 1, 2, 3, 4. So this is 1, 4. This is negative 1, negative 2. And this is negative 1, 2, 3, 4, 5, 6, 7, 2. Okay, so now we're going to graph the inverse. I'll change colors. So that's going to be 4, 1, 1, 2, 3, 4, 1, negative 2, negative 1, and 2, negative 7. 1, 2, 1, 2, 3, 4, 5, 6, 7. All right, and there we go. There's the inverse relation. Oh, no, what did I miss? Is the graph of the inverse of f of x also a function? No, it is not. Because if you put the vertical line right here, you can see that it hits the graph twice and is not a function. All right, in this story, so it looks like Chandler and Isaac. Chandler, she bikes 12 miles per hour, and Isaac does his differently, which we'll see in the next page. 12 miles per hour, so that's 12 miles. So d of t is going to represent, so the independent is minutes. That's going to be minutes biked. And the dependent is going to be the miles that you went. Okay, so minutes is in time. That's how many minutes that she's been biking. And then the miles, that is your d of t. So we do know that 12 is the amount of miles that she go in an hour. And 60 minutes is an hour. So we can assume that half of that, so that means she would go 6 miles in half an hour. We would know that if that's 6 miles in 1 hour, so 1/3 of that would be 2 miles in 10 minutes. Add one more to that makes 3, oh no, double that, sorry. Double that, so 20 is double this, so that makes this 4. This is half of this, which makes it 1. This is 1/5 of that, so that makes this 0.2 miles in 1 minute. All right, that's 1/5, same thing. Write the equation for Chandler's pacing using time in minutes as the independent variable and distance in miles as the dependent variable. So we know the starting point is at 0, and we also know that she's going 0.2 miles per minute. So 0.2 miles times t, the amount of minutes. All right, sketch the graph for this situation whose domain is from 0 to 60. So there's 0, and it's going to end at 60 minutes. So let's say this was 30. We'll call this 10. This is 20, 40, and 50. And then we've got our miles going up. So if this is 0, the most the miles was 12. So I'll say this is like 15. And I'll just go by 5s. 5, 10, 15. Okay, pretty good. Okay, so this is miles. I need to have labels. And this is minutes. Come on, pen. Alright, change the color so I go back and I can graph. 0.2 After 1 minute, 0.2. So that's going to be really, really low. And then 5 minutes was 1, 10 minutes was 2. Come on. There we go. 20 minutes was 4. 30 minutes was 6. And 60 minutes was 12. As you can see, we've got ourselves a linear function. All right, Isaac says that he calculates his pace differently. He explains that his bike is a 5-minute mile, meaning that for every 5 minutes he bikes, he travels for 1 mile. How is it different than Chandler describes his rate? Well, this is a unit rate. Instead of doing minutes per, this is minutes per mile instead of miles per minute. So that's the biggest difference. Who goes at a faster rate? Justify your answer. Okay, so now if he bikes a 5-minute mile, so that takes him 5 minutes to go 1 mile. So that means it takes him 1/5 of a minute to go, it takes him so we actually know that these two are going to be exactly the same, because a 5-minute mile, if you go back to the table here, this was a 5-minute 1 mile. So I know that they are going exactly the same speed because they actually have the same data point on the table, a 5-minute mile. So now in this case, remember we're talking about this in reverse. Whoop. So you know it's going to take them 5 minutes to go 1 mile. It's going to take them 10 minutes to go 2 miles. Double that would be 4, so that'd be 20 minutes to do 4 miles. So we know 1 minute, so that's going to be an extra 1 mile. It'll take them another 5 minutes. That'd be 25 minutes. Another would be 30, and so forth. So what we do know is that it takes them 5 times D. So it takes them 5 minutes per mile. Write the equation for Isaac's pacing using miles as the independent variable and minutes as the dependent variable. So we already have the equation, so the answer is 5 times the amount of miles. That gives you the total amount of minutes. So if I was going to graph this, so this time the amount of miles is the independent variable. So this goes 0, 1, 2, 3, 4. How high did it go? Up to 6. So it's 1, 2, 3, 4, 5, 6. And then your minutes is the D of t over here. So you notice that this graph is exactly the inverse of the one that we had made originally. So this number is going to go up to 30. So 5, 10, 15, 20, 25, 30. All right, and then I can just start graphing away. So 1 was 5 minutes, 10 was, okay, and basically it's just going to go straight across just like such. Using the equations, tables, and graphs, make a list of observations of what happens when you have two functions that are the inverse of each other. So we had two graphs. Now, was it the exact same graph? No, it was not. They were both linear, so we do notice that they're going to both be the exact same type of function. They're going to be the inverse of each other. So if you have your y equals x going straight across, you know that they're going to be equal distance going across. That's another observation. There's lots of observations you can make about these. What happens when you have two functions that are inverses of each other? So what you should also notice is that when you add up the two numbers together, that they will always equal the same. So if you the heights of each other. What do you think inverse functions have these characteristics? Well, they're opposites of each other. So they're going to be equal distance at y equals x. So they are the same graph, but the reason why we don't, I want to make this clear, we don't put them on the exact same graph because they have two different labels. The labels are in reverse. So you don't want to graph them the same. Now I know when you were finding the inverse of like 0, 60, it'd be 60, 0, but you can't just say you flip the x and the y because really they don't really make sense on the same graph because they have two different variables. The variables are in reverse. So that's the reason why we don't graph them together. Write the inverse function of this table of the values. Okay, so that's pretty easy. So the input here would be -2 and then -10, -1, -6. So as we just mentioned, yes, we are just taking the x and y's and reversing them, but we don't put them usually on the same graph because that wouldn't make sense because they have two different sets of labels in reverse. Using the points of problem 1, graph g of x, okay, in one color and the inverse of g of x in a different color. All right, so here we go. Purple, so negative 10, 2. Negative 10, 2 would be there. Negative 6, 1. 1, 2, 3, 4, 5, 6. Negative 2, 0. 2, 1. 1, 2, 1. And 6, 2. 1, 2, 3, 4, 5, 6. 1, 2. All right, so it looks like we have an absolute value function. And then the inverse. So I'm going to choose a different color. Negative 2, 10, negative 2, negative 10. Down there. Negative 1, negative 6. 1, 2, 3, 4, 5, 6. 0, negative 2. 1, 2. 1, 1, 2. 2, 6. 1, 2, 1, 2, 3, 4, 5, 6. Alright, 2, 1, 6, 2, just double check. So, yeah, I'm noticing that the originals weren't correct. So let's erase these. Negative 10, negative 2. Whoops. Different color. Negative 10, negative 2 is right there. Negative 6, negative 1. Alright, so it's linear, not absolute value. And there's your pink. There's your inverse right there. So if you remember, I said the equal heights. One minus the other is equal. Sorry, not when you add them, when you subtract them. Is the inverse of g of x also a function? Justify your answer. Yes, they are both functions because they are both passing the vertical line test. No domain has more than one range. That's just simply your answer. All right, thanks again for watching. Please give it a like to help you learn something about inverse operations, and subscribe if you haven't done so already. Thanks again for watching. Have